So, in the last lecture, we looked at evidence that proved that light acts like a wave. And we looked at like the single slit experiment, the double slit experiment, right? Taking a look at evidence that light acts as a wave. Now, in this section, this is light acting as a particle, or what we often refer to as ray optics. Now, ray optics, it's nice because you can see pretty much everything. Normally in class, we'd spend a couple days making all these images out. Since we're not meeting together, and you probably don't have all the lasers and lenses and mirrors that we have in a typical physics classroom, there's a couple videos that you'll want to end this lesson with that walk you through some of that. But before you watch this video, make sure you complete the lab on ray optics. So the ray model of light is very simple. Light when it travels, it ignores diffraction. It goes in a straight line, unlike what we talked about with the wave model of light. And this is always true as long as if there's like some type of slit that ray has to go through, or that the light has to go through, that slit is greater than at least 1 millimeter. So 1 millimeter, not a very big gap, but as long as we can go through a slit that's at least that big, light tends to just travel in a straight line. So a light ray is actually it's going in the direction that its energy is traveling, and that'll actually get us kind of into the last model of light, but it is energy that's traveling in a certain direction, and that's the direction that it's flowing. So a laser beam is what we often use in physics class, because when I point a laser and turn it on, the light has to travel in the direction that I point it, and then I see it when it bounces off the wall, or whatever I shine it at, and then bounces back to me. So that's actually what you're getting. You don't see the light. You see the light, it bounces off the object, and then comes back and hits you in the eye. And that's how you can perceive it. So the ray model of light, a couple key things with this. It travels in straight lines. Very simple. It has to go in a straight line. The speed of light is based on the material that it travels through, or the index of refraction, as we talked about last section. And light rays can cross. It doesn't really matter. They can overlap. They can interfere with each other without changing anything about it, just like sound. And we talked about that in the last unit when we talked about waves. So this is kind of a wave property, but really it's not. Light rays can cross. They travel in a straight line. Now, when light is traveling, a multitude of things can happen. We're going to talk about 4 different things that can happen. The first one is light can reflect. If you think about a mirror, the light ray, it travels into the mirror and it bounces off. And that'll get us to a key thing called the law of reflection. Light can refract. Refraction. So when I have lenses, the reason people wear glasses is because it changes how the light travels by bending it. When you're nearsighted or farsighted, I could do a whole hour-long conversation just on the concept of glasses. But when you're nearsighted or farsighted, your eye does not properly bend light to focus on your retina. So to correct that, glasses or contacts bend the light a different direction, so that it can either focus more rapidly or less rapidly to change how your retina gets those light rays. So that's what happens, and that's based on refraction. Scattering is like if light hits a particle in the air, and it just bounces off. You probably see in movies, like people go to steal something, and there's laser beam security systems, and they like spray a can of hairspray and they can see where all the lines are. That's scattering. That's just light bouncing off of random particles in the air. And then finally, we have absorption. And this is actually easy to think about whenever you're flying in a plane, and when you first take off from Glenn Mitchell International, or if you're flying like down to Florida or something, light, when we see the color of the ocean, what we see is light bouncing off. And when we're in super nice tropical places, the light looks very, very light blue because the water looks very, very light blue because the light can bounce off the sand and then kind of come back up through the water. So we see this nice blue color. Oceans look super, super dark because no light actually comes back up. It's just absorbed. Okay, so when we're looking at the ray model of light, there's a couple key things that we'll think about. But first thing we'll talk about is an object. An object is a source of light rays. So here we have like a tree, and the rays will come from everywhere on the object, and it'll send rays in all directions. Now, there's different types of objects. They could be self-luminous, meaning that they create their own light rays, or they may just reflect rays that originate somewhere else. So when we see an object, we see the light rays that are reflecting like from the sun. So that's how we're going to understand when we get into this ray tracing concept where that light comes from. So what the eye sees is they see by focusing a bundle of rays, and they do it actually right on where these light rays all come together. That's your retina, and your retina is what sends the information to the brain. So the eyes will see all these rays. They're diverging and they all bundle together because of the lens of your eye, and that's how you can see what's going on. And this is actually a common thing you've probably heard before, but we actually see everything upside down because of how the lenses in our eye work. Now, there's different sources of rays, and I already talked about it, but we have objects that are self-luminous, meaning they create their own light rays. Something like a light bulb, right? We see the light and it's making its own light. So that's a self-luminous. Or any object that doesn't create its own light, we can still see it if light reflects off of it. There's different sources of light rays. A ray source, meaning it pretty much creates one ray, one defined ray, which like a laser is a perfect example. A point source, so like Christmas tree lights, they have one specific point that they create that light, versus an extended source like a light bulb has an infinite amount of sources that create light. Or we could have a parallel ray source, and that's like a flashlight that sends out many rays of light, but still in a straight line. So we can use all of these to help us understand what's going on with light, but we're going to focus on kind of like the ray source and a little bit of the parallel ray source when we get into drawing our ray diagrams, which we're not really going to do, but we're going to watch a couple of videos that get into it. So ray diagrams is a diagram that shows us light rays in order to simplify the situation, and so we can understand what happens with an image that's being formed. In reality, there's an infinite amount of these rays, but we focus on just a couple to help us understand the basics of what's going on with image formation, which is the point of doing ray diagrams. So when we see an object, in order for us to see an object, rays from that object have to enter our eye. So a laser, we don't see a laser beam as it goes through the air, but if the laser hits a wall, that wall, or it hits off the wall, then bounces and hits me in the eye, that is when I can actually see it. So this is the case for anything that is not self-luminous, is that you have to see light bouncing off of it. And I always make this joke when I talk about this because I have my sense of humor. So if someone's mooning you, right, what you are actually seeing is a particle or a ray of light is traveling from the sun, going all the way through space, hitting them in the butt. It's touching their butt, and then it bounces off their butt and it touches you in the eye. So that's pretty gross. So we talked about these two concepts already, the point source and an extended source. They're emitting rays in every direction, and some of the rays will enter your eye no matter where it's located. And that's why we can see like a light bulb or like a Christmas tree light, and it's visible to everybody around it. So when we see objects, what's happening is that there's a ray coming down, it's hitting that object, and there's an infinite really amount of rays that are coming down, and some of those rays bounce off and they bounce off and just happen to hit you in the eye. So that's when you see something, you're seeing a ray of light that bounces off an object and hits you in the eye. Now, what can happen is this concept known as scattering, is that when a single ray can kind of hit an object and then bounce off into many different directions of weaker rays, and they leave in all directions, and that's when something hits you in the eye. So for example, when you're reading a book, every point on the surface is struck by a ray from the lamp, right? If you're reading next to a light, every single point is striking that book, and every single point on the surface is struck by some number of rays. Then, because of this concept of diffuse reflection, these rays are going to go in every direction. Some of them will enter your eye, and that allows you to read the book. But if someone else were to walk into the room and see the book, they'd be able to see that it's illuminated, that it has light bouncing off of it, because light rays are also hitting that book and hitting them in the eye. Whenever we have lasers, we only see them when they hit something and then bounce off of that. So lasers can be visible, though, when small particles such as dust or smoke or water scatter the rays in every direction through the air. So this is known as scattering. So when if you ever go to like a laser light show, they might put smoke in the air, and that allows this random scattering to happen so that we can actually see it. And again, this is more proof. This is all we're talking about, is different evidence that means, or that treats light acting as a ray. Shadows are another great examples that light acts like a ray. So if we have, here's a point source right here, right? It's shining light out in all directions. I have this nice circle here, and that circle, immediately behind that circle, what do we see? We get a shadow. And that makes sense, because if the light is traveling as rays, and there's an infinite amount, but they can't pass through this little circle here, then no light will illuminate on the screen behind it. So this is evidence that light acts like a ray. And this is from a specific point source. Now, if I have an extended source, which is pushing off light in all directions, there might be different formations depending on how the orientation is. So actually, this picture and this picture kind of go together. In position A, if the light is above the disk, because it's an extended source, we actually get light that will hit that page. B, it's kind of blocking the back of the disk, but not fully. We get a darker shadow. And then C, if it is blocking the disk, we'll get a darkish shadow. So the true shadow would mean that no light reaches it, but we get some fuzzy, darker or lighter areas around it, based on other light rays being able to hit that paper. Reflection is one of the biggest pieces of evidence of light acting like a ray. So when light comes in and hits something like a reflective surface, like a mirror, it bounces off that mirror perfectly. Both the incident ray and the reflected ray are planar points. So here, oh, I did that bad. So there's my perpendicular line. That light ray comes in and bounces off, and those are planar points. They're perpendicular to the surface. So what happens is light rays come in, they hit a mirror, and they bounce perfectly off that mirror, and that is known as reflection. Now, reflection is a very simple concept as long as I have a flat mirror, otherwise known as a plane mirror. So a plane mirror has no curves or anything like that. So if we were to look at our surface and put it flat on the bottom, we draw a normal line. A normal line just means that it's perpendicular to the surface. Whatever angle that incident ray comes in, and that is measured from normal to the ray, the exact same angle it will come out at, measured from the normal to the ray. So there's what's known as the angle of incidence and the angle of reflection. So a single ray comes through, it bounces off that surface, and it bounces out. And that is one of the simplest rules of physics, and it works for more than just light, right? If I bounce a ball off a wall at an angle, it'll bounce off that same angle coming the different way. So we have the angle of incidence, which is the angle that it comes in at, and the angle of reflection, which is the angle that it bounces out at. And the law of reflection, if these two are in the same plane, the angle of incidence and the angle of reflection, those two angles will equal each other. And this is a very important concept for us as we're trying to start these ray diagrams, to know that if I have a mirror, the angle of incidence equals the angle of reflection. That is the law of reflection. So when we're looking at things like mirrors, a plane mirror is a flat mirror. I have this object at point P. We're going to assume that it's sending out all these light waves, and it hits the mirror that's over here and it bounces off. So this is a great example. If someone's standing in front of a mirror, you can go up to them, behind them, and you would see exactly what they see. Now, if you look at different angles, you might not be able to see exactly what they see because you can't get those light rays to bounce off and hit you in your eye. So when you're looking in a mirror, though, what you see, you're the object, what you see is on the other side of the mirror. So you look at the mirror, your image is on the other side of the mirror. It appears to come from beyond the mirror. And this can get kind of confusing. We're not going to get super in detail with it, but this is how we can understand what formations happen. And when we look at mirrors, and if you've ever been to a fun house and they got all the different mirrors, they manipulate this mirror right here to change what happens to the image that's being formed, and you look weird. So what you can see is the actual image. Now, there's a couple other things that we need to set up. The object distance is how far away you are from the mirror. The image distance is how far away the image is from the mirror. Now, in a plane mirror, these two are exactly the same because it's a nice flat mirror. So the image distance and the object's distance will be the exact same. And what you see then, so here we have an object and it's hitting a mirror. Now, if we were to draw our reflected lines, they go off and hit you in the eye. If we trace these backwards, that is where they appear to come from. So even though this tree is on the same side as you of the mirror, it appears to come from the other side of the mirror. So that's more evidence that light acts like a ray. So rays will reflect off and spread out, and when you pick up those rays, when you see those rays, that's how you can see the image that's being formed. But you can't always see the full image if you don't get light rays reflected. So you can play around with this. If you got like a bathroom that's got a mirror in it, have someone stand in front of the mirror. If you stand directly behind them, you should be able to see them. But as you start to step off to the side, the further and further away you get from the side, the less and less of them you'll be able to see, because light rays won't be able to bounce off of the mirror and hit you in the eye. Now, the other key thing with ray tracing is this concept of refraction. So there's reflection and there's refraction. So here I have an incident ray, a ray that's coming in, and it's hitting what's known as a prism. Now we can see that some of that light, not much of it, but some of it does get reflected. But we can also see that as it changes into this prism, or as the light travels through the prism, it bends. It was going this way, and now it bent a little bit. And then when it leaves, it bends again. So the light refracts. Part of light gets reflected, and then part of the light goes into this new medium, this new N, right? Because we talked about that last week. And it's transmitted through, but it changes a little bit of its direction. And that is known as refraction. So when light comes from the sun and hits water, for example, it refracts. This is just a picture of it, right? There's a refraction of all these different beams of light and then there's a refraction from a point source. But when light changes mediums, it bends, it refracts, and that's what glasses are, right? It's a change in medium. It's the lens, plastic, whatever it's made, glass, whatever it's made out of. It changes direction, and that's what corrects your vision. So there is just like we had the law of reflection before, there's also some important stuff to help us understand the law of refraction, but it's a little bit more confusing. We still draw this normal line going through the surface. The angle of incidence is measured from that normal line. Now, we used to measure this angle right here, and we said, oh, that's the reflected angle. Well, yes, some of it's going to get reflected, but some of it will also get transmitted, and it'll bend. So theta 2 here, this is the angle of refraction. So there's an angle of incidence, and instead of an angle of reflection, there is an angle of refraction. And we still measure it from the normal line, except now the normal line is right here, whereas before we used the same normal line before and after. And similarly, if we're coming from water going into air, I still have my normal line here. Here's my angle of incidence. Here's my angle of reflection. So theta 1 and theta 2. And that's any time that the light changes mediums. Now, to mathematically quantify this, we use what's called the law of refraction. And I'm not going to ever sit and have you guys calculate refracted angles and stuff like that. But N1 sine theta 1, that is the first medium and the angle of reflection. N2 in sine theta 2 is the second medium and the angle of refraction. So we can use Snell's law to figure out exactly how much light gets bent. Why is this important? Again, it's more evidence that light acts like a ray versus acting like a wave. If it was a wave, there wouldn't be any bending. The wave would just continue to travel. So Snell's law shows us that when a ray is transmitted into a higher index of refraction, it'll make a smaller angle. And if it's transmitted into a lower index of refraction, it'll make a larger angle. And this is how lenses use the bending of light to refocus light on your retina. So the biggest thing about ray tracing is actually doing ray tracing. And all I gave you was kind of a crash course in evidence that light acts like a ray. So there are 3 videos. And in these 3 videos, this guy goes through and he talks about mirrors and reflection. He talks about refraction, and he gives you a little bit of lenses and images. So light, when it goes through or bounces off different things, changes how the light travels, and then that changes what we see. So we talk about mirrors and we talk about lenses. And these are different ways to see what happens as light travels as a ray. In mirrors, we have the plane mirror, we have a concave mirror, and we have a convex mirror. And if we had class time, we'd be playing around with all these, and you get to mess around with how that light bends and talking about those things. Lenses, there's just concave and convex lenses. And he's going to talk about those in the video as well. Concave, essentially, it doesn't matter if it's a mirror or lens, but if something's concave, it looks like this. This is a concave mirror or a concave lens. And what happens is, as light travels through that, it bends in different directions. And in this case, concave mirrors and lenses spread that light out. Then we also have convex. Convex lenses look kind of like that. As light travels through, though, all that light converges to one point right here. So mirrors and lenses, he'll show you a little bit of those, and you'll get to check that out in the videos. So you should have already completed lab point 2. filled out this graphic organizer as you went through this lecture. Then there's a couple questions for homework week 7, giving you just a little bit of practice with this concept of light acting like a ray. Next week, there will be a mini lesson on the photon model, and then we'll be taking the test. The test is very, very, very conceptual. Very conceptual. We're not going to get into specifics with this unit, but just hopefully you can understand the 3 different models of light. And after this week, you should have been good now with the basics of the ray model of light. If you have any questions, always feel free to reach out.